All right. Hey everyone, my name's Rob Hamilton. I'm co-founder and CEO of AnchorWatch. We're doing custody tech bundled with insurance for Bitcoin and cold storage. And the talk today I'm going to be doing about is Miniscript. The journey to it was kind of funny, seeing Vic here. The whole journey started when one day I was having a conversation with him about wanting to build custom scripts. And he said, Rob, you're great, you're smart, you're not that great, you're not that smart, just use Miniscript. So that was a little over a year ago, and I wanted to kind of take this talk today to talk about my experience with it, click a little bit deeper into semantically how it works under the hood, and kind of some war stories and just things considering if you're building applications leveraging Miniscript. So yeah, general Bitcoin script introductory just to kind of set the table, and then thanks to Lisa for doing back-to-back-to-back Miniscript talks today. So Randy's going to be going on after this, Miniscript for developers, and then Sanket's going to be doing Miniscripting in Covenant World. So it'll be a fun, exciting afternoon for me. I don't know about all you. And it's very humbling to be on a stage like this at Bitcoin++ with such visionaries changing Bitcoin like Junseth and many others. And today I'm going to be keeping it at a very constrained level about what actually works in Bitcoin consensus today, and leaving the wizards to unlock the next stage of scripting so we can kind of revisit all of this. And then I'll be teeing off a couple basic examples and then going through some Bitcoin script stack and some application learnings of how to actually kind of leverage this stuff in production and thinking about how you design good user experience and how you do your own design trade-offs. So super high level Bitcoin script, the rules that encumber how you can spend a Bitcoin transaction, single SIGs, multi-SIGs, HTLCs. Script is valid when it's terminating and something other than zeros at the top of the stack. And then there's a lot of things that can get it to fail. If you end in zero, if you use a verify function and you fail it, like time locks or signature, check sig verify, exceeding the script stack size limit, an individual element being over 520 bytes, using disabled opcodes, and as well as combining epoch and block time locks, because either you're using end sequence or you're using end lock time, depending on what kind of time lock you're leveraging at the transaction or the input level. And the way the interpreter parses that, you can't simultaneously be, say, under 500 million for a block height absolute time lock, as well as over 500 million for an epoch timestamp time lock. That's just mathematically impossible, so it's something that you're kind of constrained against. So the goal here is being able to do leveraging the core security primitives in Bitcoin, your signatures, hash locks, and time locks, using absolute and relative, but either block height or epoch. I call this, you can only bring one clock. And then using kind of very straightforward semantics like and, or, and thresholds. And the goal is also that you have discrete satisfaction conditions. Just because you have a script that works does not mean that there could be unintended ways, and I'll be showing an example of that later. So very simple examples, and this is often when people ask me about use cases, things that come very straightforward of what we kind of call a decaying multisig, where you can have a 2 of 3 that becomes a 1 of 3, or a 2 of 3 that becomes a 2 of 4, right? Basically leveraging more Bitcoin script to be programmable money today within the consensus rules in a safe, analyzable way. Also, as a fun trivia fact, when I was going down this rabbit hole, you can do Lightning Network Bolt 3 invoices that are actually more on-chain efficient than the Bolt 3 spec today. Not saying that everyone's going to rewrite Bolt 3, but it's just an interesting consequence that the compiler is very efficient at being able to derive efficient scripts. So on the left here, we have BDK Playground. It's a great website on the Bitcoin Dev Kit website. It's a WYSIWYG. You can drop in kind of custom policies, and it'll spit out an output descriptor. So this is a Miniscript policy. Super human readable. You can diagram it out and do it in more detail. This is an example here of a 2 of 3 that becomes a 1 of 3 after block height 52,000. And then there's an alternative path here that could be a 2 of 2 after block height 1,000,000. And the one thing additionally to call out here is that you have these conditional weights, which actually we'll show some examples later of how that gets impacted for efficiently stacking this on chain to take as less bytes as possible. If you know a condition is less likely to be satisfied, you can rearrange your script in such a way that on average you're going to be spending less bytes when you're actually constructing the transaction. So going through the compiler, you take the text that we had on the previous slide over here, and you get a lot of new things you may not have seen before. Or underscore I, and underscore V, there's colons, right? S colon, like there's a lot of things here. And at first this was overwhelming, being like, okay, I understand that this should work, but what does it actually mean under the hood? And it's turned into, if you've ever seen that scene from The Matrix where Cypher's sitting in front of the computer, he's like, oh, I just see blonde, brunette, redhead. And now all I see is, and underscore V, wrapped fragments, right? So I'm going to talk a little bit about my journey of kind of actively just throwing a lot of examples against the wall, spinning some stuff up testnet, looking at the script stack, and kind of deconstructing how that all works. So there's the 4 core correctness properties of what you're expecting. Type B is like the parent canonical one you should always be aggregating to be valid Miniscript. It's a very discrete sense that you're either going to meet the satisfaction condition and you're going to have a 1, or you're going to fail it and you're going to make 0. You can apply modifiers though. For example, V, if you're using a verify function. This is important to understand because rather than pushing an element, you're either passing or failing, right? So you're either satisfying or dissatisfying a time lock, or an op-check sig verify, which is going to be different semantically with how the script is going to be executed on the stack compared to just a regular check sig. Additionally, you have key operations. I have an example here, just like doing a public key hash check. You're going to be doing signatures with the key fragment. And then the wrapped one is your op swap and your alt stack gang, where you're actually doing script manipulation of where you're going to next in the stack. And this is all important for one of the core principles of Miniscript is you have these composable policies, and you're going to be able to take one example, like output descriptor that's leveraging Miniscript at the policy level. You should be able to combine that with another one. So you can take one really elaborate vault construction and a second one, and you should be able to combine those two together and know that they can all aggregate up. But you have to keep track of where you are in the stack and how all that logic's executing. So from there, those are like the kind of 4 parent ones. There's modifiers that change how these types behave. Z being 0 arg. You're not consuming anything off the stack. By default, this is just the nature of a time lock. Leveraging op-nop, you're not actually modifying where you are in the stack. Next one would be you're consuming one element, right? A hash lock, where on net you're going to be consuming one element of the stack. Non-zero, there's going to be at least one. Really straightforward example of this is a multi-sig, where if you have a 2 of 3, you're going to be consuming all of those public keys and the signatures that are all being taken off the stack. Additionally, another one that you wouldn't think immediately of is dissatisfiable, and it's understanding that this condition can always find a way to be satisfied in how you're executing. And a perfect example of how this doesn't work is a time lock on its own, because if the time has passed, you can't go backwards in time and dissatisfy that condition, right? But keys, you can just pass in 0 for a key value. You'll know for always be able to have a way to dissatisfy that fragment. Additionally, no time lock mixing, so assigning type K and making sure that you're not using both epoch timestamp as well as block height within a fragment, within an output descriptor. And then finally, unit, just being able to say, like, if this is satisfied, I'm just going to get 1 on the stack, which is important for a lot of how the logic works under the hood for aggregating conditions. You're often running a counter, and you want to be able to know that I'm just going to have 1 that pops out at the end here. And then some contextual ones, L and U for likely or unlikely. This always comes up in OR fragments, and this goes back to that optimization for understanding what's more likely not to happen. But when satisfied, you're just putting 1 on the stack. And then your alt stack, calling out that you're explicitly going to be calling to the alt stack for this operation, and I'll be showing examples of this in a moment. Finally, malleability, I touched on this before, it's just very important, and the one bug that the Miniscript compilers had up to this point was a malleability bug, and I'll show an example of what that original script stack looked like. You want to be able to understand that a signature is being required to satisfy an individual fragment, and that there's the forced dissatisfaction, which ties back into time locks. You can't always forcibly know that a time lock will be dissatisfied by default, because if time has passed enough, then it's valid. And then finally, the expressive element for script components, ensuring that there's unique ways to invalidate it. I'm going to show that a previous example we had and kind of talk a little bit how these fragments work under the hood. So the OR I one that you see before is now just saying if X, else end if, right? And whatever that X is in this case, the first one is actually going to be the recovery keys, which if you remember from the policy was less likely to happen it gets put in first because you can quickly just skip all of this by pushing a 0 and kind of moving on. And then the threshold one's pretty straightforward, intuitive. You're just kind of adding up signatures, going to the end. And then the swap operation, if you're going down here, I'll show the full example in a moment. You'll see that's kind of going from alt stack, and total stack to kind of push and pull things as a counter. And then this is a really important element here for the time lock condition here. It's talking about this is the likely path to execute between the two, as we mentioned before. Additionally, the end modifier is really critically important because it actually is to show that it uses op0 not equal. And what that does by default is whatever element came before this, we're going to push 1 if it's not 0. Otherwise, we're going to push 0. And this is a really important mitigation for the malleability effect I'm going to talk about. So this was originally, I think, as of Miniscript version 7, a valid Miniscript output descriptor. But it was found that by default, it was assuming the properties of taproot. So in BIP 342, the minimal if rule is that op if functions are only going to assume 0 or 1. That is only a policy, though, when it comes to SegWit and legacy scripts. And this allowed a malleability attack where I actually had to go, they removed the original blog post off the BDK website, but you can kind of pull up, they were using this as a reference example. A miner could actually, once this was broadcast to the network, you would be able to redirect the output. You can RBF it or just kind of invalidate the previous transaction and just push it as your own. And you could intentionally fail all of these signature checks, and you would be able to just push in a number that satisfied the threshold, and it would be able to actually be spendable on the network. And this was all because there was the assumption that the D wrapper had the property of U, which is unit. You're always going to get 0 or 1, but that's not the case because the minimal if rule wasn't enforced for SegWit. So kind of going through a little bit of the high-level example, I'm just going to talk a little bit about what we're thinking about when it comes to leveraging Miniscript and using more advanced kind of on-chain custody solutions. This is a Miniscript template that we're pending right now, but finalizing around this idea of a combination. It's like a joint custody model. And the reason why it's joint custody is we're going to take a lot of these different combinametrics of time locks and or conditions and conditions and add a lot more robust flexibility to how we can spend. So there's ultimately 3 parties here, but there are 4 set of keys. I should have mentioned this earlier. You can't, for satisfaction, you cannot use the same public key at multiple places because you can't know for a fact if I use the same public key, what branch or what kind of part of the script I'm intending to execute on. So I have this towards the end, but a principal, I use this in the framing of a principal agent problem. You would have a principal, whoever the customer is, would have 3 keys. A primary agent, primary point of contact would have 3 keys. You'd have a secondary agent for recovery purposes, for emergency recovery. And then finally the recovery keys. And ultimately what you have here is the recovery keys are the principal keys, just using a different derivation path. So it's the same person who's kind of managing both of these. And this works in a really interesting ensemble where you have a customer, a primary point of contact, like an emergency contact, and then your sovereign exit path. The way we're leveraging this as it intersects with our product for insurance is that if we have a set timeline and date of understanding when your insurance contract will expire, there's a mechanic called a tail where there's open liability, but after that ends, there's no longer a contractual arrangement. The default state, if we cease to exist, should be you should be able to recover your money again and not have to talk to us. And that's how we're able to enforce that here. Kind of going through the logic layers here, at default, it's a 2 of 3 of the principal, a 2 of 3 of the secondary agent, and there's no time lock condition. Next one is actually leveraging a decaying multisig, where if the customer were to lose 2 keys, we could still use one of their keys and use the smallest epoch timestamp, the one that's soonest to arrive, to allow it to become a 1 of 3 from the customer and a 2 of 3 from us. Finally, in the event that the customer has lost all of their keys, we as the primary agent can work with the secondary agent to be able to execute a transaction to be able to recover the funds. And then finally, after everything terminates, you're able to go to a sovereign recovery path. So looking at this as a policy, you can see it being visually represented here with the description of the actual policy itself. You can see the 2 of 3. This is how you properly would execute a decay multisig. is that you have a threshold of 2 total conditions, but you have 3 keys and 1 time lock. And then you have this 2 of 3 of the primary agent, and then you have an OR wrapper for either the recovery partner or the customer, and then finally the recovery keys at the end with the lower weight satisfaction. So this is what it looks in here. I put in some just human readable, just like timestamps to show what it looks like, and I'm going to show over the next couple slides to break this down. It's a big script, 730 bytes, 245 V bytes. This was on testnet a couple months ago. And I'm going to go through what this actually looks like on the stack. So by default, it actually starts with the sovereign recovery path. And you'll notice immediately we're using public key hashes instead of public keys. And so if you know 99 times out of 100 you're never going to have to materialize that key, you actually save a lot of space on chain by just putting a public key hash there. Right? So this is one of the things that Miniscript just automatically handles under the hood. But if you start semantically analyzing and looking at these scripts, you can start intuiting out why these decisions were being made. So you have that OR operator first. So the first is OR, the recovery path here, and then you have your 3 keys here. The threshold argument here, well, it's an OR rested with an AND. So the OR, if X, else, and if. And then AND is you're just analyzing both of those, and you have to successfully pass both of those conditions to continue. Now, the threshold function actually has the V property because we are using a time lock, so there's actually a verify check. You can fail this if you don't satisfy that condition, and that's part of the logic and how you construct this. You're then pushing your public key hashes to the stack. You can see that the second and third recovery keys here have the property A, and that's because it's actually going to go down and call the alt stack to kind of park values as an aggregator. So if you're going through this, let's say you satisfy this first one, you get a value of 1, you put that to the alt stack. You're then doing another public key hash check. Let's say you fail this one, you complete that, you go back, and then you're pulling that back from the stack, and then you're adding those 2 together, so you have 1 and a 0, so now you have a total of 1. You push that over to the alt stack again. You go through the rest of your math, and then you can get to your end condition. And then you then have your 2 equal verify. You verified you satisfied 2 of the conditions for the 2 of 3. And then you run a check for the timestamp to make sure with the op check lock time verify. And if you were to walk through this, February 1st, 2023, is this an epoch time? And then in Little Indian, it encodes down to the 80ABD963. So that's just the one check. If you were to pass a 0 and kind of move on, you don't have to worry about it anymore. This is the other 3 conditions. Going through this here, you have your AND condition, right? You're kind of satisfying multiple things. The primary agent as well as one of the other conditions. The one mistake I have here in this is the time lock is on the primary agent. It should be on the customer, but it's a small mic, sorry. You're going through that AND operation again. You're running, again, you have a threshold with a time lock, so you have the V flag against it. And you're just pushing keys to the stack. This time, though, you're actually using op swap to kind of just push down the next 2 elements of the stack, kind of run through your signature checks, aggregating them all, and then you're running your time lock here. And this is really an important detail, is that the time lock condition now has the N property, which on stack as a Miniscript fragment is 0 not equal. So when you get to the point where you can't just push an arbitrary, if I pushed an arbitrary value at this point and it got through to the stack, it would automatically compress it down to the value of 1, which prevents you from being able to do that malleability attack that we saw in the earlier slide where I could just push any arbitrary value to the stack and trick the script into satisfying the condition even though I have none of the private keys. And then going through this would be the customer by default object multisig for the 2 of 3. And then finally, if that doesn't get satisfied, we are down to the object multisig. So if up, so if, I'm blanking on the spot. If you were to go through this and you satisfy the condition, you're good. You kind of go to the end. If you have the value of 0, though, you weren't able to satisfy this multisig, you actually go down to this final path here. And again, it's also not as likely to happen by default. You go to a public key hash, and then you would do the time lock check. This is for the emergency layer where the customer lost all their keys. And so you start, like, this was kind of part of my journey, was kind of throwing random arbitrary things all over the place and seeing how it all clicked out onto the stack. When it comes to actually building this stuff, leveraging Bitcoin dev kit's been, we're a very small engineering team. It's been massively powerful for us to be able to stay lean and kind of build out a full fleshed out wallet with all the supporting features. And it's built on top of Rust Bitcoin and Rust Miniscript, which allows us to kind of upstream and kind of channel all of this really powerful primitives in a really strong Swiss Army knife. If you're going to use time locks, I think the idea of using time for your security in Bitcoin is incredibly powerful, but you have to pick your UX poison. Because your two options are using a relative time lock, which means if you have multiple UTXOs in your vault, each one will have different spending conditions that are possible, right? If I sent you money today and I sent you money next year, they're each going to have different rules. And that's a rough understanding because people think this is my wallet, I can spend it under X conditions, but now there's a relative condition that governs some of your deposits but not some of your others. Additionally, opcheck sequence verify for relative time locks only goes out to 15 months. 65,536 blocks, right? And that's for a lot of people when they think about long-term storage, they may not want to have to go to their keys that often. Your alternative, though, is an absolute time lock, which means whatever date you're setting in the future, you have to do an on-chain transaction to refresh those time locks. So you have to kind of really think about how you're designing a user experience and what is kind of if you're going to leverage this, how do you want to kind of execute on that? Next are, I call xpub shenanigans, and this goes back to the point before, you can't duplicate a public key within an output descriptor that's leveraging Miniscript because you can't guarantee which path you're satisfying. And so the Liana guys came up with this idea for your BIP32 paths to actually, your first key using 0 and 1 for receive and change, and then you can use that same key again but use 2 and 3, and you can actually use that key in multiple places, which is a handy way to not have to worry about multiple devices or multiple backups, but you can have the same wallet be able to spend and execute and sign off on different branches depending on what BIP32 path you're using. Next would be avoiding ORs. I've noticed this a couple times working with people that are building on this, is they'll just throw OR statements everywhere for decaying multisig. So they'll say OR like 5 of 7, or 4 of 7, or 3 of 7. And you just very inefficiently stack stuff on chain. So usually the move here is just to drop your thresholds in the policy generation with time locks inside of them, and just doing the math and understanding how many ultimate conditions you want to satisfy and padding it out from there. And then the last two would be constructing PSBTs. Miniscript is great for automatically handling all of the witness construction, but you still need to be able to kind of communicate with it to understand which, if you're presenting someone with an unsigned PSBT, by default, you don't know what path you're going to be executing on. BDK does this really well with hash maps for being able to kind of walk down, so each wallet has unique keys for how they're being able to spend that. For user flows, though, by default, how wallets work today, you just export your PSBT, but now you have to have context in how do you plan on executing this. Ultimately, it wouldn't matter because if you got the signatures anyway, you could put them into a finalizer, PSBT finalizer, and kind of kick everything off. But if you want to make it as streamlined as possible, it's just a nice way to keep things clean. And then finally, Miniscript templates was an idea that kind of came out after Bitcoin Miami last year in 2023. And the ultimate goal was just, if there was a general reference point for hardware wallets, software developers to kind of document how they're doing this, to kind of unify user experience, small real estate screen on hardware wallet devices, and kind of like having a good reference point. There's a Blockstream repo here if you're interested. I think the deck gets it out after this. And I've been toying around with trying to properly codify and lead by example for how I'm thinking through documenting this stuff. Because it's also important for having general reference descriptors for if you have for some reason, partial recovery, you don't have to reverse engineer the entire script. You can understand, okay, my timestamps are always going to be either noon or midnight UTC, like a basic example, right? Even though you can use any possible second, constraining that space would probably be helpful for standardizing how people would expect time locks to be run. And that's it. Any questions? Yes, Reardon. It could be done. So by default, Miniscript isn't leveraging code separator. So I don't see why you couldn't just go about doing it that way. That's a good point. Yeah, I'll have to think on that. Sorry.
Yeah. How
Oh, debug them. Yeah, absolutely. Yeah. So the first question was using opcode separator to instead of doing the xpub trick to kind of point to where you're looking to spend from. The next question was how do you debug these? So by default, the debugging it depends on where you're trying to debug it. If you're creating a policy, the compiler will just reject something that can't work, right? A very simple example is if you just created a script that was just a time lock, right? You have to have signatures to be able to prevent malleability. You just won't be able to do it. Additionally, the compiler it's like a goalie. It's not going to let you do something that has those mixed time locks, right? You would have to be manually trying to like get around that, but if you're using the compiler, that'd be the first thing. So if the next question though, if you're having an issue debugging downstream, like once it's being built out and you're like sending and moving around transactions, for me, I haven't had issues at all for once something gets compiled, finding some way to spend it. Typically, it's just maybe I'm not encoding the right variable for a private key or something. I need to rearrange things around. I use tools like BIP174.org, which is great for just dumping in a PSBT, and you can actually look at the partial signatures that are there. And at least by default with BDK, you actually it'll map also the BIP32 paths, so you can say like, okay, this key is associated with this device. Let me make sure that I have all of that key information aggregated properly. That's usually when the transaction construction change may have miscoded something, so a key isn't being properly passed along with the signature when it should be. But those are usually the main points. The good news is that if it passes the compiler, you don't have to worry about it. There is a known way to satisfy that, assuming you have the private keys and or the time has passed and or you have the pre-images for your hashes. Yeah. Yeah, so the question is when would one want to kind of go directly into the Miniscript logic itself as opposed to working things at the compiler level? I personally wouldn't do that, only because the amount of time to review if you start changing the properties to know, like to have the knowledge to know that you're not modifying a behavior property in such a way where maybe you introduce malleability or maybe you create an unspendable script. I know Jeremy Rubin has messed a little bit with the Miniscript compiler on his side to do like stuff with Sapio, and then he put ordinals and inscriptions in there. So I guess that would be like if you want to be on the frontier and do something new. As far as I'm concerned, for like layer 1 Bitcoin custody, it does exactly what I need it to do, and the last thing I'm going to have the hubris to do is start getting in there and messing with it myself. Yeah. Yes. Yes, when taproot. Yeah, so that's actually a really great point. So tap Miniscript, you can kind of, every single time you have an OR statement, you just put in a different tap leaf. For us, I'm hoping to by the end of this year. I'll be honest and say that BDK doesn't support like advanced tap scripts yet, so I haven't touched it that far. I know the Liana guys just pushed out tap script support for their stuff. And what's really cool about TapScript too, like an unintended consequence, is you can leverage different time locks. You can mix clocks because they're not going on the stack at the same time for the interpreter. Last year at Bitcoin++, Super Testnet did on-chain hash bets where you can go long and short, and you would just put in using TapScript, what do you think is going to be satisfied first? A certain time being hit or a certain block number being hit? And that's a really fun, creative way to do that. And it's only going to be possible if you're using TapScript, so you're not combining time locks on the stack at the same time. Yeah. It does exist, yeah. And I think Salvatore, I'm not sure if he's here right now, he added it to Ledger. I think the cold card now, I think it is now. Yeah, so we have cold card and the Ledger, which has support for it. The other Miniscript enabled wallets is first there was the Spectre DIY, there was the Bitbox02, the Blockstream Jade, the Ledger, and the cold card. And then also, I guess technically also the tap signer, if you wanted to count that as well. Yeah. Yeah. Yeah, so the BDK right now for the taproot descriptors, it'll do taproot single sig, and I think it does basic multi-sig. Yeah. Yeah. I'll have to give that a look, but yeah. Cool. Thank you. Oh, I am hiring, so if you're looking for a job, let me know.